this is engineering mathematics. Now we're interested in boundary conditions for diffusion type problems. First we'll discuss three types of boundary conditions. Number one, U equals G of T, and that's temperature at the boundary. And number two is du by dt plus lambda U equals G of T, and this is temperature of the surrounding medium. And which is specified N is the outward normal to the boundary, where N is the outward normal to the boundary. And 3 Gu by Gn equals G of T, and this is the heat flow across the boundary, which is visualized here, it's drawn pictorially. And the ends of the rod follow temperature curves G1 and G2 of T. An apparatus that keeps the ends at a specific temperature is called a thermostat. Now, similar boundary conditions also apply to higher dimensional problems in 2D, below for example here. Now imagine the problem of finding temperature inside a circular disk when the boundary temperature is specified in polar coordinates to be U, R, theta and T equals cosine T of sine theta, and which is graphed here. Now the initial condition would vanish over time, and the resulting temperature inside the circle would depend on the boundary conditions. Now the temperature of the surrounding medium is specified. Again, take our copper rod, but instead of having a specific temperature, G1 of T and G2 of T, we only bring them into contact with the surrounding mediums that have those temperatures. Now suppose the left side is enclosed by a container of liquid with changing temperature, G1 of T, while the right end is enclosed in another liquid with a temperature G2 of T. Which is drawn here, the rod is insulated laterally. Now, specifying these types of boundary conditions, we cannot say the boundary temperatures of the rod will be the same as the liquid temperatures at G1 of T and G2 of T, but we know by Newton's law of cooling that whenever the rod temperature at one end of the boundary is less than the liquid temperature, then heat will flow into the rod at the rate proportional to the difference. In other words, for a 1D rod with boundary conditions at x equals 0 and L, Newton's law of cooling states that a outward flux of heat at x equals 0 equals L here of U of GT, U of GT minus G1 of T. Now, an outward flux of heat at x equals L equals L U of LT minus G2 of T, where H is the heat exchange coefficient. I've put in a box here, outward flux of heat across a boundary is proportional to the inward normal derivative across the boundary. Now this law says that it keeps increasing rapidly in the direction outward from the boundary of D. And then heat will flow from the medium into the domain D. In our 1D problem, Fourier's law takes the form here, where outward flux of heat at x equals 0 equals K, partial derivative of U with respect to x of our theta in T, and likewise for our is minus K for our boundary condition L of T. Now I've drawn here du by dn is greater than 0, which means heat flows in, and this one likewise is less than 0, and it means heat flows out, and this is hot and cold. N is the outward normal. Now du of dn is the change in temperature in the direction of n. Now this is just an illustration of Fourier's law. Now partial derivative du by dn equals minus du over d minus n. Now the derivative of inward normal is negative of the derivative of outward normal, which that's basically what that means. Now when K is the thermal conductivity of the metal, which is a measure of how well material conducts heat, Fourier's law holds for anywhere inside the rod and not just the boundary. Now inside the box here, I've put the flux of heat crossing x of naught from left to right equals here minus k of a du by dx of x naught of t. And I've drawn it on a little graph here to help visualize this. Now Fourier's law says that if u of x of naught of t is less than 0, then heat flows from left to right. Likewise, if it's the other way around, then the heat flows from right to left. Heat flows from a high temperature to a low temperature, which this is basically what I'm saying here. Now finally, if we use A and B, the assumptions for heat flux, we have boundary conditions for our rod given here, where u du by dx of 0 and t are boundary conditions given here, and likewise for L of t here. Or we write h of k as lambda. So boundary conditions for the heat flow across the boundary are given here. In higher dimensions, we have boundary conditions. For example, if the boundary of a circular disc is interfaced with a moving liquid that has a temperature G theta of T, our boundary conditions would be written as such. Here, the U by dr, R of theta of T, is the outward normal derivative in the positive R direction of U evaluated at a point R theta on the boundary. This is linear non-homogeneous due to the term here, G of theta and T. The type 3 condition, the flux specified, including the special case of the insulated boundaries. Insulated boundaries do not let heat pass, and hence the normal derivative inward-outward must be 0 on the boundary, since all normal derivative is proportional to the flux. In the case of a one-dimensional rod with insulated ends at x equals 0, x equals L, the boundary conditions are given here. In 2D domains, an insulated boundary would mean the normal derivative of temperature across the boundary is 0. For example, if the circular disc were insulated on the boundary, then the boundary conditions would be such that U of R theta t equals 0 for all theta contained within 2 pi and 0, and all t contained within infinity to 0. On the other hand, if we specify the amount of heat entering across the boundary of the disc, the boundary condition is this, where F of theta of T represents the amount of heat crossing into the circular disc from an outside heating source. We now illustrate different types of boundary conditions. Type boundary condition for 1D heat flow. Suppose we have a copper rod of 200 centimeters long that is laterally insulated and has an initial temperature of 0. Suppose that the temperature of the rod at x equals 0 is insulated, while the bottom at x equals 200 is immersed in a moving water that has a constant temperature of 20 degrees. Now we've drawn it pictorially here, which is laterally insulated. Now given our conditions here, boundary conditions, and at x equals 200 we're plugging in these values, the mathematical model would be the 4 equations with initial conditions at 0 degrees, and x is between 200 and 0. Now alpha equals 1.16 centimeter squared per second, and this is the diffusivity of copper, and K is 0.93 calories km per second. Now this is the thermal conductivity in copper. H is the heat exchange coefficient. Now note a typical heat flow problem with a square, which is drawn here, and these are our boundary conditions. This represents the insulated boundary, and this likewise is the amount of heat crossing the boundary, and likewise for the other side, which is a surrounding medium. Now the typical boundary conditions for diffusion in a square. In this problem, after we specify temperature, In the diagram we take over for t containing infinity and 0, and determines the subsequent temperature values of u of x of yt. Whatever temperature, however, it must satisfy the boundary conditions in the figure above. Note the boundary conditions given here on the circle will not require boundary temperature to be g theta t, but when heat exchange coefficient H is large, the boundary conditions essentially says that the boundary temperature U of R theta T is almost equal to G theta T. Please do like and subscribe, I've got plenty more to come.